Okay, so hi everybody. So here's a link to the YouTube stream that I just posted. Okay, so it's lecture 15, and this is the last lecture on counting, or explicitly about counting. Counting is going to come up in a big way when we talk about probability. So let me do it like this. Okay, so it's lecture 15. Oh, I don't know what happened to the pen. And today we're going to do three things. So we're going to finish talking about permutations and combinations with repetitions. And then we're going to talk about a different type of situation in counting that comes up a lot, which is ways to count, the number of ways to put a bunch of objects in boxes. So putting objects in boxes. So this is in contrast to so far where we mostly talked about how to arrange boxes, either in a sequence, in which order does or doesn't matter. But then we're going to talk about another situation. And then finally, I'm going to talk about a very important, powerful principle called the Pigeonhole Principle. Which is deceptively, useful. It's extremely simple, but very useful and cool. So let me first do this. So recall last time we talked about in the last couple of lectures, we mostly talked about arrangements of R objects chosen from a collection of N objects. And there were a couple of variations of this, which it's useful to organize in a table. So I'm just going to draw a table here. And really the variations, there are two questions you should ask. One is, are repetitions allowed? Okay, so these R objects are distinct. Sorry. No, the R objects are not distinct. The N objects are distinct. So repetitions allowed, yes or no? And the other question is, does the order matter or not? So are we counting ordered objects or unordered ones? So if repetitions are not allowed, so all the R objects are distinct, then and the order matters, then the answer is the number of permutations, P and R. If the order doesn't matter and repetitions are not allowed, then the answer is N choose R. And then if repetitions are allowed and the order does matter, then we figured this out in the last lecture. The answer was, well, for each of the R positions in the arrangement, you have N objects to choose from, and by the product rule, you get N to the R. So this was quite simple. And now we're going to answer, well, what goes in this box? What happens if the order doesn't matter and repetitions are allowed? And the motivating example for this, if you recall, was how many different ice cream sundaes how many different 5-scoop sundaes can you make from 3 given flavors, which were mint, chocolate, and vanilla. And the important, the important thing about this problem is that the order of the scoops doesn't matter. It's just how many ways are there to select 5 scoops from these 3 flavors. So this is, the clarification here in the context of counting is that these are unordered. And we saw last time that there is not really a way. Oh yeah, somebody's asking if Wi-Fi is malfunctioning. So actually, my Wi-Fi was malfunctioning, and I'm actually on tethering right now. So I think there is something wrong with the campus Wi-Fi. But anyway, so last time we saw that you can't do this with the product rule. So we couldn't use the product rule. Sorry, the division rule last time. And so now we're going to solve this problem by appealing to a different perspective, which is actually quite useful. So here's the idea. Yeah, the key observation is that a sundae is completely determined, is completely determined by the number of scoops of each flavor. Okay. And so what that means is that if I have a particular sundae which has, I don't know, like three scoops of mint and 1 scoop of chocolate and 1 scoop of vanilla, then all I really care about is these 3 numbers here. Okay, I'm not sure what's going on with my highlighter here, but okay. All I really care about is these 3 numbers, right? 3, 1, and 1. And the important thing is that these numbers add up to 5. And so the important insight here is that any such description of number of scoops is in 1-to-1 correspondence with an arrangement of putting of the following kind. I'm going to create 3 boxes labeled M, C, and V. Okay. And then I'm going to start off with 5 tokens, 1 token for each scoop. And then I'm going to put the tokens in the boxes to indicate how many of each scoop I want. So for example, the arrangement on the left corresponds to putting 3 tokens in M, 1 in C, and 1 in V. Okay. So what's this object on the right? Well, this is an arrangement or an allocation of 5 tokens, which are indistinguishable. They don't have names. Into 3 boxes, which are actually distinguishable. Right? The 3 boxes have labels: mint, chocolate, and vanilla. The balls don't have labels, or the tokens, or whatever these are. So that means if I want to count the number of sundaes, I can count the number of allocations of 5 tokens, 5 indistinguishable tokens into 3 distinguishable boxes. So any questions about that? I'm not done yet. I haven't counted the ladder, but what I've essentially done is provided a bijection. Okay. So we have that the number of Sundays is equal to the number of allocations of 5 tokens into 3 boxes. And implicitly, what's going on here is that there's a bijection, right? That's what I'm saying when I say that a Sunday is completely determined by the number of scoops. This is a bijection. Okay, so now I have to count the number of ways to put these tokens in these boxes. And here I'm going to do something that seems a little bit absurd, but it really works. Is I'm going to say, well, you know, what if I look at an allocation like this? But then I erase the edges of the outer edges of the outermost boxes. Okay, so I only keep the well, okay, let me draw a clearer picture here. Or let me actually make a copy of it so I can. So the second observation is that if I take an allocation of tokens into boxes, there's a one-to-one correspondence between such arrangements and you know, arrangements that look like well, okay, let me just do it like this. Let me just squish the boxes together. And then let me erase the edges on the side. And the edges on the bottom, and just keep the dividers. Okay. Now, what is the object on the bottom? So it's easy to see that all 3 of these pictures contain the same information. If I give you any one of them, you can construct the other 2 uniquely. Right. So the picture on the bottom, the ones tell you, you know, how many M's there are, how many C's there are, and how many V's there are by just, you know, they divide the zeros into 3 different sets, into 3 groups, and the total number is 5. But what kind of object is this thing on the bottom?
It's a bit string.
It's a bit string with exactly 2 ones. So what I'm really saying in this observation is, so formally what I'm saying is allocations of 5 tokens into 3 boxes are in bijection with 7-bit strings with exactly 2 ones. Right? So these 2 ones are really special. They correspond to the dividers in the allocation in boxes. But you can see that this is a bijection, right? Each one uniquely determines the other one. And now, well, how many 7-bit strings with exactly 2 ones are there?
7 choose 2.
7 choose 2, because all you have to do is choose the position of the 2 ones. And so the conclusion is that this is equal to the number of 7-bit strings with 2 ones, which is equal to 7 choose 2. So this is another bijection. This is the second observation. These are not complicated bijections, but they're really kind of clever. They require a real change in perspective. And so what's the conclusion? Well, the number of Sundays is 7 choose 2, which is, I mean, I don't know, what is it? I guess it's like 7 times 6 divided by 2, which is 21. So there are 21 different Sundays you can get. So any questions about this example?
Does this mean that you have to have at least one of each flavor?
No, because the ones could be right next to each other.
Oh, okay.
Right? So there's no
Okay,
constraint.
okay.
If the ones are right next to each other, it means, well, it means that one of the bins is empty. One of the boxes is empty.
Thank you.
Yep. It's always good to, I mean, we've stated that these things are bijections without writing a formal proof. And this is one of the reasons why counting is tricky, that often you'll very implicitly say something is a bijection, and you better be sure you're right. If it's unclear, it's better to write, really prove it's 1-to-1 and onto, but I won't do that for now. So what's the general theorem here? Well, I mean, okay. There are actually two theorems here that I want to state, or I'll just state it as one theorem with two parts. The one is the number of ways to place n indistinguishable objects into k boxes is n plus r minus 1, choose r minus 1. Okay, and the reason for this is that this r minus 1 is the number of dividers in between the boxes, right? If there are, sorry, k minus 1. If there are k boxes, then how many dividers are there going to be between k boxes? They're going to be k minus 1. So let me actually just write that like this. So okay, let me write the proof. The proof is that the allocations are in bijection with n plus k minus 1 bit strings with exactly k minus 1 ones. Ones which correspond to the dividers between the boxes. And then the second theorem, the second part of the theorem, which is just an immediate conclusion of this, is that the number of ways, the number of R combinations of n objects with repetitions is n plus r minus 1, choose r minus 1. And the reason is that these combinations are in bijection with the box allocations above. with allocations of n objects into R boxes. So the answer to this question is that going back to this table, what goes in here is n plus R minus 1, choose R minus 1. So that's a summary of permutations and combinations with repetition. The most interesting one was the last one we did, and we had to make this connection to putting objects into boxes. So any comments or questions about this?
May I see the form, like the small form for order and repetition?
Excuse me, I didn't understand.
So like there's a small form for yes and no, like the order and repetition.
Oh yeah, right. So what do you want to see here?
Yeah, just want to make sure it's
Yeah. Okay, so I'm gonna put a copy of. I'm gonna make a summary of all this on the last slide, because one of the confusing things about this chapter is that there are a lot of different variations. So it's nice to have a summary of counting formulas. So I'll just make one here. So these are the formulas for arrangements of R objects chosen from n objects. Okay, so now I'm going to talk about a slightly different setup, which we already just saw, is a number of ways of putting objects into boxes. And here, here I would say that there are two different variations. So let's motivate this with an example again. So here's an example. The example is how many ways? So how many ways are there to deal 4 hands of 5 cards each from a deck of 52 cards? So hands are unordered. So the order of the cards doesn't matter. Well, actually, you know what? Maybe I'll do this example second. So let me move this to the next slide. I'll do this later. Okay, so maybe the first thing I want to say about putting objects into boxes is let's make another table. So now we're going to count allocations of n objects into k boxes. And again, I'm going to make a table. And the first question is, are the objects distinguishable? Okay, so another distinguishable is just another word for, can you tell them apart, or are they labeled? The book also used the word labeled. And if they are distinguishable, then we're just asking that, okay, we have these n objects labeled 1, 2, 3 up to n. And we want to put them into k boxes, which are also, the boxes are always labeled 1, 2 up to k. And we're counting the number of, two allocations are different if you can tell them apart. And since the balls have labels, the only two allocations are different. Two allocations are the same if and only if you have exactly the same balls in exactly the same boxes, or I guess objects. This is often called balls and pins. The book calls them objects. I'm just calling them objects. So if these are distinguishable, how many ways are there to put these n objects into these k bins? Well, okay. Can somebody think of a process for putting these n objects into k bins, which uniquely defines the allocation?
We're gonna assign each object a bin.
Yeah,
So-
you just go through the objects one by one and give each one a bin. So for the first one, there are k choices. For the second one, there are k choices. You might put it in the same one. For the third one, there are again k choices. And so in the case of distinguishable objects, you have n choices, one for each object, and k ways each. And each different way of making the choices gives you a different allocation because you can tell the objects apart. They have labels. So the total is, quite boringly, k to the n. So this is just k to the n. And if they're not distinguishable, then we actually just solve the problem above in the theorem, right? If you want to put n indistinguishable objects into k boxes, it's n plus k minus 1, choose k minus 1. So we already solved this. Okay. So any questions about this piece of this diagram? Okay, so there's one more variation which comes up when you're putting objects into boxes, which is, are there any constraints on how many objects you're allowed to put in each box? So the second variation is you add a constraint that the ith box for I going from 1 to k must have some fixed number ni objects. Okay. So the second axis I'm going to put here is there a constraint? So this is if there are no constraints. You can put as many objects as you want in each box. And the second column is going to be, you insist that there are n1 objects in the first box, n2 in the second box, up to nk in the third box. So I'm going to start off with what I think is the easiest case. The easiest case is actually this. How many, suppose I have a bunch of indistinguishable objects. So they're just like, you can't tell them apart. And I have k boxes, and I tell you I want, 5 in the first box, 2nd in the third box, and 10 in the last box. How many ways are there to do that?
Just one, right?
Just one, yeah. The problem is completely determined, right? You have to put n1 in the first box, n2 in the second box, n3 in the third box, and the objects are all the same. They're indistinguishable. It's only one way. So this is kind of boring. Now the last case here is kind of interesting and corresponds to this example that's here. How many ways are there to deal 4 unordered hands of 5 cards each from a deck of 52 cards? Okay, so this problem, okay, there are no boxes or yet in this problem. And often, the trick in counting is to see that this corresponds to a problem of putting some objects in boxes. So does anybody have an idea of how to do that? Maybe somebody who hasn't answered in a while.
So would it be that you have boxes and 5 like tokens?
Okay, so one idea is you have how many boxes?
5
5 boxes.
and then 4 tokens.
4 tokens. Okay. Okay, let's think about that. So what do the tokens and boxes correspond to?
So you have like 5 cards, or sorry, you would switch them, right? Yeah, sorry, you would have 4 boxes and 5 tokens, so that way the 4, each hand would be a box, and then each card would be a token.
So hand 1, hand 2, hand 3, and hand 4. Okay, but maybe you didn't understand the problem. So there are 5 cards in each hand, and there are a total of 52 cards. So I'm not handing out 5 cards to 4 people, right? I'm handing out 52 cards to 4 people. So I'm not quite seeing how it's going to work out with just five tokens, because I actually have a lot of choices to make here, right? I have 52 choices. For each card, I have to give it in some hand. So do you want to rethink how many tokens or how many boxes there are?
Would it be 20 tokens then?
Why would it be 20?
Because you each have like because 5 times 4 is 20, so you have like 20 cards total that can go to all the people.
Okay, that's an interesting thought. So you have 4 hands and you have 20 tokens, and these correspond to the 20 cards that you're actually going to deal, right?
Yes.
But which 20 cards are you going to deal?
I suppose you don't know, right? Because they come from the 52.
Right. So remember yeah, okay. So there are a couple of ways you can do this. One is you can first choose the 20 tokens, so maybe tokens is not a good word because they're actually distinguishable, right? They're cards. So four cards, let's say, or well, okay, 4 distinguish or 20 distinguishable, 20 labeled tokens, let's call them. So indeed, this can be made to work. You could do step 1, choose 20 cards out of 50. And then step 2 is put them in the 4 boxes. But there's actually kind of a slicker way to do this, which I'll just tell you. So your idea can eventually work, but here's a slicker way. So we won't do this. The slicker way to do it is to say, I'm actually going to make 5 bins. I'm going to make 1 bin just for the rest of the cards. Okay. And now I can have all my 52 cards as tokens. So 52 cards as labeled tokens, or let's just say 52 cards, right? So these are all labeled. And now I just want to put these 52 cards in these 5 boxes. Okay. And within, so I have to keep all of this stuff clear, that the cards are distinguishable. Within a hand, the order doesn't matter. And obviously the order of the rest of the cards doesn't matter either. So let's try to find a process for choosing such an allocation. So any thoughts on what the first step of the process would be?
Take 52 minus the 20 cards factorial and put that in the rest. So it'd be 32 factorial for the possibilities for the rest.
Okay, so you're kind of starting with the rest, and you're saying there should be 30. Okay, so okay, so you could actually choose the rest first, but I think you're saying 32 factorial. That kind of suggests that you care about the ordering of the rest. You don't really care about the ordering of the rest, right?
Oh yeah, so it'd be 52 factorial over 20 factorial. Or no, 52 factorial over 32 factorial.
Yeah, I think what you're shooting for is 52 to choose 30. There's that many ways to choose the rest of the cards.
Yeah.
Okay, so that's correct. But again, so that's correct. But it turns out there's actually a way to do this, which gives you an even nicer formula, which is to choose the hands first before choosing the rest. Okay, so you're on the right track. Just basically choose the amounts to put in these bins. So first step is choose 5 cards for hand 1. Sorry. Let's call this H1. And there are 52 choose 5 ways to do that. Okay, so we're done with the first hand. The order doesn't matter. And now what's the second step going to be?
There are 48 cards left, so it'll be 47 cards left. So
yeah, exactly. So choose 5 cards for H2 given H1. And the point is that H1 always has 5 cards, so this one is always going to have 52 minus 5, so 47, choose 5 cards. And then next you're going to choose 5 for hand 3. That's going to be 42, choose 5 cards. And then next you're going to choose 5 for hand 4. So that's 42 minus 5, that's 37, choose 5 cards. And then finally, you got to choose the rest, right? And this is why I did it in this order. So this is choose 32 for the rest, right? But now, how many cards are left? 32. So 32, choose 32. And the reason I did rest at the end is that this is just 1. There's only one way to choose the rest of the cards. So while your suggestion was correct, it turns out to be nicer to choose the rest of the cards at the end because you don't care about them and they're uniquely determined after you choose the cards that you're actually going to deal. So now what's the total number of ways to choose the cards? So how am I going to combine this information to get the total number of ways?
Multiply them.
Yeah, because the number of choices in each case is always the same regardless of what the previous ones were. So this is 52, choose 5, times 47, choose 5, times 42, choose 5, times 37, choose 5, times 1. Which, let's expand it out. This is 52 factorial over 5 factorial over 47 factorial times 47 factorial over 5 factorial times 42 factorial times 42 factorial over 5 factorial times 37 factorial times 37 factorial over 5 factorial times 32 factorial. And now, the beauty of this is that there are a lot of cancellations. So this 47 cancels this 47, these 42s cancel, the 37s cancel. And you're left with just 52 factorial over the factorials of all the sizes of the bins. 5 factorial, 5 factorial, 5 factorial, 5 factorial, and 32 factorial. So that's the total number of ways, and so that's the total number of poker hands, which is a very large number. I'm not going to compute. And so the point of this example is, this is an example of putting 52 distinguishable objects into 5 distinguishable bins. But the order of the objects in each bin, in each box, doesn't matter. That's the key. So okay, so maybe I should say the key in this thing is that the order of objects in a box doesn't matter. And so the general answer to this, the exact same proof will give. So in general, there are n factorial over n1 factorial, n2 factorial, all the way up to nk factorial to put n distinguishable objects into n distinguishable boxes with ni in the ith box. And of course, in order for this to work, the sum of the ni's has to be equal to n, right? Otherwise it, the total number doesn't add up. So provided n is equal to n1 plus n2 all the way up to nk. So this is the general theorem. The proof is the same as above. You can read it in the book if you want. You just write down, you look at this process, you write out the factorials, you get these cancellations, and you get this this expression. So the answer here is n factorial over n1 factorial, n2 factorial, all the way up to nk factorial. So this is a summary of how to count the number of ways of putting objects into boxes, depending on whether or not there's a constraint on the numbers and on whether or not the objects are distinguishable. So any questions or comments about this?
Just wondering in general for these types of questions, if we put our final answer as like what you had here,
Yeah,
like 52.
That's fine. Yeah.
Okay.
Yeah. I don't expect you to do this huge arithmetic, to like figure out what these giant numbers are. So wait, so maybe I should okay, that's not. Yeah, okay, why not? I'll just do this. And I guess I'll erase this stuff here. So that's a summary. That covers most of the formulas. That covers the most commonly used formulas that appear in counting. Either arrangements of objects or allocations of objects into boxes, either distinguishable or not distinguishable. And the order in a box doesn't matter.
So like constraint is like there's restriction in like arranging them into boxes, like every box needs to have something, right?
Yeah, so you can call this like a frequency constraint, or I don't know, just a count. Yeah, every box needs to have a particular number. Yeah, that's what I mean by the constraint. Okay. There's one more example in this. So the thing is, the trick in these problems is often just to identify what are the objects and what are the boxes. So let me give you another problem, another example, which is not obvious. It's not clear that it's related to boxes at all. The example is how many distinct words can be made by rearranging the word anagram. So this is a word with 1, 2, 3, 4, 5, 6, 7 letters. And so how many words can you get by rearranging this? Any thoughts?
Would it be 7 factorial over 3 factorial?
Okay, yeah, exactly. So you absolutely jumped to the correct answer. So here's a one answer. Well, it's 7 factorial. That's just a total number of words by rearranging 7 symbols. But then, you know, A appears 3 times. And so for every word that you get by arranging these, you're gonna end up overcounting by 3 factorial, because this is the number of arrangements, number of ways to arrange the A's. So this is by the division rule, right? So this is the number, total number of permutations. If you treat the A's distinct, if the A's were distinguishable. But they're not distinguishable, right? The A's are all the same. So you have to divide by the number of ways of rearranging the A's. So that's one answer. Here's a second answer, which is related to objects and boxes. It's a little bit surprising. But what I'm going to do is I'm going to make a box for each position. Each position 1, 2, 3, up to 7. Okay. And now make a token, make a labeled token. Or sorry. Oh no, sorry. I've got this wrong. Make a make a token for each position. So yeah, this is always a little bit confusing. Make a token for each position, 1, 2, up to 7, and these are distinguishable, right? Because the positions are really not the same. You can tell them apart. And now make a box for each letter. Each letter A, N, G, R, and M. Okay. And now I claim that words that you can make out of these letters are equivalent to allocations of these tokens into these boxes, where the A box has 3 tokens and all the other boxes have 1 token. So number of words is equal to the number of allocations with 3, 1, 1, 1, 1 tokens. Right? Because I mean, it's a bit of a weird way of thinking. I'm thinking, for each position, I have to assign it a letter, right? So that's fine. I have to put it, that corresponds to putting it in a box. And I know I have 3 A's, so I have to assign A 3 times. That's why I get these frequencies. But now, according to the previous formula, this is 7 factorial over 3 factorial times 1 factorial, 1 factorial, 1 factorial, 1 factorial, which is the same answer, 7 factorial over 3 factorial. So I got the same answer in 2 different ways. In one case, I used the division rule. In the other case, I observed that this kind of problem of creating letters is actually an assignment problem, where I can think of it as putting these. Well, the tricky thing is the objects you're putting in the boxes are positions. But nonetheless, this is. So a lot of these problems, the interesting part is how do you set it up as a problem about putting objects into boxes. Any comments or questions about this? Okay, and I'll make one remark. We only talked about the objects that we're putting in the boxes being distinguishable or indistinguishable, right? The boxes were always distinguishable. So you can ask the question, what happens if the boxes are indistinguishable? If the boxes don't have labels? So if the boxes are indistinguishable, well, there are actually no formulas. There are no formulas. So there are no expressions you can write down that tell you what it is. So this is a little bit surprising, but it really makes the problem much harder. And so this will be skipped in the course. So boxes will always be taken to be distinguishable. So any questions about this? Yes.
Would you be willing to give an example of a problem with indistinguishable boxes? Just
Sure. Indistinguishable boxes. So, well, I mean, you can just ask the question, how many ways to put, I don't know, let's say 10 balls into 3 boxes, and everything is unlabeled, right? So you have these 3 boxes, but they're not labeled MCV or with letters or anything. And you have these 10 balls up here, and you have to put them in the boxes. Well, how many ways are there to do that? Or, a more mathematical problem is how many ways to write 10 as the sum of 3 integers. And now, the 3 integers don't have names, so the order doesn't matter. These are actually the same problem. So this is studied a lot in number theory, and it's a very interesting function, but there's no formula for this. If you give me an integer and you ask how many ways are there to write it as a sum of 3 integers, it's actually not easy to know that.
Awesome. Yeah. Thank you.
Okay. Any questions? Yeah, there are a lot of variations here, so maybe this I find particularly useful, just to keep my head straight about what the different variations are.
Is token the same as like boxes that you're writing?
No, tokens are objects. So objects could be anything. They could be balls, or they could be tokens, or they could be cards. The word boxes is reserved, though. The boxes means the order of the objects in the box doesn't matter.
Okay.
And this side you have arrangements, this side you have allocations. I mean, arrangements means you're putting them in a sequence. Either the order matters or doesn't matter. Whereas the right-hand side is a more nuanced way of saying, the order doesn't matter inside the boxes, but the boxes are distinguishable. So, yeah. And, and I mean, you can probably see, in fact, these are related, right? The way we derived this formula was by turning it into a problem about putting objects into boxes. Okay, so that's all I want to say about putting things in boxes. And now I want to talk about one more truly amazing principle of counting called the Pigeonhole Principle. Section 6.2. So here's a theorem known as the Pigeonhole Principle. Let me write it the same way the book writes it. Yeah. So if k is a positive integer and k plus 1 or more objects are placed in k boxes, then there is a box that has 2 or more objects. Okay, so the picture is, okay, you have k boxes, and you have k plus 1 objects. So in this case, k is 4. Then if you try to put these objects in the boxes, one of them is going to have 2. It's kind of obvious. But since it's so important, let me tell you the proof. Proof is by contrapositive. So assume every box has at most 1 object. Well, there are k boxes. So how many objects can there be?
K objects at most.
Yeah, every box has at most 1 object. Since there are k boxes, there are at most k objects, which means, strictly less than k plus 1. So it's not hard to prove. Okay, how could something so trivial be useful? So let's see. Any questions about the statement before we look at some applications? Okay, let's see some consequences of this. So we'll start with some kind of obvious ones and go to some less obvious ones. So yeah. So here's application 1. It says okay, in every group of 366 people, 2 people have the same birthday. Okay, what are the objects and what are the boxes in this to get this from the pigeonhole principle?
Shouldn't it be 367?
Oh, are there 366 days in the year?
Well, it could be like leap
You're
year.
right. You're right. It could be a leap year. Okay, fine. You're right. So 367, yeah. So proof, the objects are people, boxes are 366 days of the year, and apply the pigeonhole principle. Okay, not surprising. Okay, let's see something a little more interesting. Second application is if 5 integers are chosen from the set 1 to up to 8, then 2 of them must add up to 9. Okay, so there are so many ways of choosing 5 integers from the set. Actually, how many are there? 5 distinct integers.
You choose 5.
8 choose 5, yeah, which is quite a lot. So we're saying the order doesn't matter. You choose 5 integers from the set, then 2 of them have to add up to 9. Any thoughts on how to approach this? So the creativity is how do you figure out what the box is and what the objects are? Any ideas? Let's just throw around some ideas. So I don't want to just write the answer down. Let's just, let's try to see if we can discover it.
Would the boxes be, so we'd have 4 boxes, and then the first one is 1 and 8, the second one 2 and 7, the third
It's a
one
great idea. Yeah.
3
So
and 6, 4 and 5.
exactly. So observe that these integers, that the integers 1 through 8 can be partitioned into 4 pairs, namely 1, 8, 2, 7, 3, 6, and 4, 5, such that each has, so these are 4 disjoint, right? No integer appears in both of these, such that each one sums to 9. Okay, so now make a box for each pair. And now by pigeonhole, if you choose 5 integers, some box has to contain 2 integers, right? So by pigeonhole, any 5 integers in this set must contain 2 in a box, and then these 2 integers have to add up to 9. So I'd say the creative part here was this, right? That observing that you can do this partitioning. And then you have to make a box for each pair. Any comments on this? Okay, let's do something even a little more interesting. So application 3 is actually the Chinese remainder theorem for 2 equations, which we already proved, but let's prove it again. So it's a statement. So assume m and n are positive integers that are relatively prime, and a and b are some integers between non-negative integers that are strictly less than m and n respectively. Then there is an integer x such that x is congruent to a mod m, and x is congruent to b mod n. So you remember this, I suppose. But now and we proved it using a somewhat clever proof, actually, involving inverses and so on. But let's prove it again using the pigeonhole principle. So here's the proof. So here's the proof. So consider the integers a0 is equal to a1 is equal to a plus m, a2 is equal to a plus 2m, all the way up to a sub n minus 1 is equal to a plus n minus 1m mod m. Just n minus 1m. So how many integers are there? There are n of them, right? Consider the n integers. So these are n numbers. Okay, so there are n numbers. And now I'm going to look at their remainders modulo n, right? So create n boxes. So maybe I'll do it like this. Bi, which is going to be the set of integers. Let's just call them x, such that x is congruent to I mod n for I going from 0 to 1 all the way up to n minus 1, right? So the remainder modulo n goes from 0 to n minus 1. So there are n boxes. Okay, so this is not such a great situation for applying pigeonhole, right? If I put n integers into n boxes, I'm not going to get a collision, right? But actually, maybe I should have said, what am I trying to do? I'm trying to find an integer which is congruent to A mod m and congruent to B mod n. And so so notice that all of these AIs are all congruent to A mod m for all I less than n minus 1, right? Now, if one of them was congruent to B mod n, then I would be done, right? If one of these AIs was congruent to B mod n, then I would be done. So I'm going to do the sneaky thing. I'm going to assume that none of these are congruent to B mod n. So assume for contradiction that all of these numbers are not congruent to B mod n for all of these I. So this is the key step. Okay, so I have n integers. They're all congruent to A modulo m, and none of them are congruent to B modulo n. So when I put them in boxes, how many boxes am I actually going to use?
N minus 1 boxes.
N minus 1 boxes, right? Why?
Because we've got n boxes, except we're gonna not place anything in the bth box.
Exactly, right? So really, what I'm going to do is I'm going to create n minus 1 boxes for I going from all the way up to n minus 1, except I equals B. So I'm just not going to consider integers congruent to B modulo n. And now, because of my assumption, I can place these n integers into the n minus 1 boxes, right? So we place each AI in its box, right? So each AI lies in Bj for some j, but by pigeonhole, there are n minus 1 boxes and n integers, right? So by pigeonhole, there is some j such that sorry, there's some j and some indices I1 and I2. Such that AI is congruent to AJ is congruent to, oh, sorry, not A. So this AI1 is congruent to AI2 is congruent to J modulo N. Right, so the picture is I had originally these N boxes. But one of these boxes contained B and I deleted that box. And now I put these N numbers into the other boxes. So one of these boxes has to have 2 numbers. But now this is going to be a contradiction, right? So why is this a contradiction? Well, this implies that N divides AI1 minus AI2. And this is impossible if I choose AI1 to be, let's say, bigger than AI2, because this difference is less than N. Well, okay, which I leave. This is just some. So let's see here. So N divides AI1 minus AI2. Right. Let's just write out what that means. That means N divides A plus some I1M minus A plus I2M. Right. So which implies N divides I1 minus I2M. But M and N are relatively prime, which implies N divides I1 minus I2, since GCD Mn is 1. But this is impossible since I1 minus I2 is less than N. Okay, so this pigeonhole can be used to prove the Chinese remainder theorem. Any questions on this proof? So yeah, I kind of wrote the proof in a non-linear way because I kind of wanted to see how you could maybe try to derive such a proof. But yeah, really, the first thing you do is you assume for contradiction that it's false, and you use this contradiction to reduce the number of bins, and then you apply pigeonhole, and then you get another contradiction. So therefore, this has to be satisfiable.
For the last part, how could you? Yeah. So, so is it just we can assign M into these 2 parts, or like, and
sorry, could you repeat the question?
So the sentence thus implies the one after it, A plus.
So this sentence, the first one, is a definition of AI1 congruent to AI2 modulo N. Or that's something we proved, right? If X is congruent to Y mod N, then N divides X minus Y.
Oh, yes. So previously when you wrote A0 equals to A1 equals to A plus M, so that's why.
Yeah.
Right. Yeah. So
I defined the AIs over here, right?
Got it.
Yeah. So then I plugged that in here, and that's how I got A plus I1M, A plus I2M. Okay. And finally, let me give you one last. I'll just state it. I won't do the proof since, well, the proof is more about graph theory than about pigeonhole, but it uses pigeonhole. But I'll state it, and you can read the proof in the book. It's not long. Here's the proof. So here's a statement. In any group of 6 people, there are either 3 mutual acquaintances, so 3 people who know each other, or 3 mutual strangers. Okay, this is a fact, this is a theorem. Anytime you have 6 people, either 3 of them don't know each other at all, or 3 of them all know each other. Now, okay, the proof is in the book. It's based on the Pigeonhole Principle. It's actually based on something called the generalized Pigeonhole Principle. Which says that if you put n objects in k boxes, some box has at least the n over k, the ceiling number of objects. And this is just a fancy way of saying there's somebody who's at least as big as the average. Right, n over k is the average number. That might not be an integer. And since the objects are integral, you can always round up to the integer above that. And this is an example, this is maybe the most well-known example of an area called Ramsey theory. Which roughly says that if you look at any structure that's big enough, it has to contain some patterns. It has to contain some coincidences. And so one way people describe this is that is a total disorder is possible, is impossible, right? So total disorder is impossible. Or large enough objects must contain patterns. So this is a very specific example of that. Anytime you have 6 people, there's a pattern. Either 3 of them know each other or 3 of them don't. And many of these things follow from the Pigeonhole Principle. And I'll end by saying that there are a number of fascinating open questions in this field. So let me just add a page so I can say that. Okay. Right. So here's a theorem which we won't prove. The theorem is for every n bigger than 1, there exists some number r such that in every group of r people, there must be n mutual acquaintances or n mutual strangers. Okay, so what that means is that you can think of this r as now that there's a function r of n. For every n, if you look at a large enough group, you'll see this pattern involving n people. So for example, it's known that what we just showed is that r of 3 is 6. That's what's written above, right? If you take 6 people, you always find a triangle of people who all know each other or who don't. It's known that r of 4 is 18. Anytime you have 18 people, it's either some 4 of them know each other or some 4 of them don't. R of 5 is actually unknown. Nobody knows what it is. People have worked on it for decades, but it's somewhere between 43 and 48. And of course, R of 6, et cetera, are totally unknown. So this is what I mean by total disorder is impossible. If you have a large enough object, some piece of it must have a very specific pattern. And that's kind of what we've seen in all of these applications of the pigeonhole principle. I mean, the number theory one, maybe not so clear, but in this is a simple example of that, right? If you take enough numbers, then some two of them have to have some pattern. If you take enough people, some two of them have to have the same birthday. Anyway, that's all I want to say about that. So thanks.
Thank you.